High-voltage electrical grids are engineered to withstand the most extreme terrestrial conditions, but they were not designed for the physics of a geomagnetic storm. This map illustrates the Hydro-Quebec system. Because primary generation is in the remote north, power travels over 1,000 kilometers to reach southern population centers. To maintain stable voltage, the network relies on strategically located static VAR compensators, or SVCs. While this vast footprint allows for massive power generation, it also makes the grid behave like a giant antenna, capable of capturing electromagnetic disturbances occurring far above the atmosphere. On March 13, 1989, a severe magnetic storm struck Earth's atmosphere. This created intense Earth surface potentials, a shift in the electrical charge of the ground itself. Standard power systems use deep grounding wires to protect against rogue electricity. In a typical scenario, like a lightning strike, the wire directs the excess current down into the earth to be safely dissipated. The March storm reversed this flow. The disturbance induced a direct DC current in the soil, which traveled upward through grounding wires into the transformer neutrals. Inside, this steady push of DC clashed violently with the grid's oscillating 60 Hz alternating current. The grounding wires, which were built to be the grid's primary safety release, had become the entry point for the geomagnetically induced currents. To see what happens next, we have to look inside the iron core of a power transformer, where the transfer of energy depends on a delicate magnetic balance. Normally, the alternating current creates and releases magnetic flux in a continuous, balanced cycle. The core magnetizes and demagnetizes 60 times every second. The invading DC current causes asymmetrical saturation, constantly adding magnetic flux without allowing it to release. Pushed to its absolute magnetic limit, the core can no longer absorb energy. Incoming alternating current hits this barrier and distorts, unable to pass as a clean wave. The solar storm did not need to physically break the transmission lines. It only had to alter the magnetic properties of the iron cores the grid relies on to function. Because the transformer core can no longer handle the power smoothly, the blocked AC energy is forced into new, jagged frequencies, known as harmonic currents. This recording shows the result. The expected smooth 60 Hz sine wave is replaced by second, third, and fourth order harmonics. These spikes represent extreme electrical distortion. Traveling onto the 735 kilovolt transmission lines, these harmonic currents created severe overvoltage peaks across the network. As these jagged waveforms pulsate through the system, they generate rapid thermal stress in the physical conductors and equipment. These distortions were now moving directly toward the SVCs, the very devices responsible for maintaining the grid stability. The geomagnetic disturbance had effectively transformed the grid's own power into a destructive frequency, heading toward the most sensitive voltage control systems in the province. The harmonic currents hit the capacitor branches of the SVCs first. Because capacitors have naturally low impedance to these specific high-frequency harmonics, the currents were magnified. This created a resonant condition that pushed the electrical flow far beyond normal limits. Monitoring these systems are protective relays, automated computers programmed to detect standard faults, like short circuits or overloaded lines. The relays identified the harmonic resonance as a terminal equipment failure. Following their programmed logic, they triggered an immediate automatic system shutdown to protect the SVCs from physical damage. In doing so, the automated safety systems disconnected the very equipment required to prevent a total voltage collapse. The collapse was nearly instantaneous. In less than a minute, 7 critical static VAR compensators were tripped offline by their own protection logic. Without the SVCs to regulate voltage, the system fell out of step. This map shows the result: the separation of the Legrand network from the rest of the province and the immediate loss of over 9,000 megawatts of power. The entire province of Quebec was plunged into a blackout that lasted more than 9 hours as engineers worked to restore the system. We have spent decades mastering our defense against visible, physical threats like the ice on this traffic light. But to maintain a stable modern grid, we must now account for the invisible, mathematical consequences of space weather.